Markov chain Monte Carlo. What I'm going to do is I'm going to start just by giving you the algorithm, as I mentioned, and then afterwards work backwards to explain why it actually works. So the algorithm itself, the point of it is to simulate random variables from a given density. They'll come from that density, they'll be identically distributed, but they won't be independent from each other. So they won't be like a traditional sampling method, which is where you get IID-ness. It won't be IID. So what do you have to what are the inputs for the method? Firstly, you have to specify your target. So this is known up to a normalizing constant. So you don't have to know the density exactly. You just need to know, some scalar multiplied by the density. This actually helps in a huge way. Secondly, you need to have this thing called a transition kernel. So what that is you're going to be creating samples by making a sequence of points, and you need to be able to propose, I'm at this point here, and need to suggest another point somewhere else to try. So this is, I've written it here as Q of y given x, as kind of like a conditional distribution, and that's what it is actually. So given, so how it'll work is given some xi that I've simulated, let's call it xr, then we'll plug that in to this transition kernel, and then we'll have a density with respect to the first argument here, and we need to be able to simulate from this density to get the next sample, xr plus 1. So what does this look like as an actual example? So say we, for whatever reason, wanted to simulate from the PDF, which is something multiplied by 2 plus sine x over the range x is 0 to 4 pi. So that would be our target density up to a normalizing constant. So here I've written this is proportional to this symbol. And then the proposition, the transitions that we propose are, given that I'm at x, I'll suggest that y is a random point which is uniformly distributed but centered on x. So it'll go up to 1 less and up to 1 greater than where we were before, and just pick uniformly between that range, choose a y. So that's what it looks like if you were to sample this thing, but with the transition kernel, you also need to be able to write down this density. So this particular distribution, y given x, this is what it looks like. So the indicator that your y is within a distance of 1 from x, and then this divide through by the normalizing constant. And then same as every other algorithm, we need to say where are we starting and how many replicates that we want to create. So where we start, that is important, not super important as we'll soon see, but that does have an influence on how your algorithm progresses. And yeah, R is just some big number. So this is the main algorithm for the MCMC, the Markov chain Monte Carlo, named after 2 of the inventors, Metropolis and Hastings. If I remember correctly, I think this was invented during the atom bomb project, which I've forgotten the name of. Operation Atom Bomb, at the end of World War II, and the Americans invented this. Oh, Manhattan. Your memory is much better than mine. Thanks. So how it works is, so here I've written again the inputs that we need to give it, f of x, the target, the transition, starting point, the number of replications. And then the last thing is we need to make this definition. So this alpha of xy is the acceptance probability. And so it's going to be, between 0 and 1. And the way the algorithm works is similar to what I showed last time of acceptance rejection. So to generate the rth random variable, we plug in where we were last time, xr minus 1, into the transition kernel. And then from that, we have a density, and we simulate from that density. So we simulate a proposed point y, which is sort of a suggestion for what the next sample would be. It's not necessarily the next sample, but it's like a proposal, it's a suggestion. And then you plug in where you were last time, your proposed point y, and then you calculate this alpha, the acceptance probability, and with that probability you accept the change. You accept that my new point will be the proposal y, and then with probability 1 minus alpha, you reject it and you stay, in that case, you stay where you were last time. So the next sample will be the same sample that you were on last time. And so in more of an algorithm kind of way to look at it, it's just on the right here. So for a for loop, r equals 1 to capital R, sample y from our transition kernel, sample just a uniform random variable, calculate this acceptance probability, and if my uniform random variable is less than that, set xr to be y, otherwise xr is xr minus 1. Okay, so let's see how this actually works in practice. So this is some simulation of the MCMC algorithm at work. I'll change it back to a more basic example. So what's happening here is we're sort of looking down on a two-dimensional distribution that we're trying to sample from. So the curves here are the contours of a PDF, of a joint PDF in terms of x1 and x2, and we're trying to sample variables. So this is the area region of high interest here in the middle of the banana, and then as you get further away, those samples should appear less often. And so what the algorithm is doing is it's taking, now let me slow it down somehow. So wherever it is now, it suggests a point as a proposal. So it samples from the transition, which is, in this case, it's just proposing points that are normally distributed, where the normal distribution is centered on where we are now. So it's a random walk. That's what these circles are saying. This is sort of the contour lines of the Q transition kernel. And so it samples where we are, it samples the proposal y. That's what it's drawing the black line towards the proposed point. And then with some probability, it either accepts the point, in that case the line turns green, and then we move to that point. So all these are failing, yeah. Or it rejects the point and it stays where we are. So here, this particular sample has been done like 10 times now in a row. And if you look down the bottom, what it's doing is it's showing you a histogram of the marginal histogram. So, sorry?
Like a marginal distribution for
Yeah, exactly. So each axis is sort of all the points are being dropped down here, and it's showing you what, if you were to get the sample, what does it look like? And then I don't know if it's easy to see, but there's a small curve also for what it should be, what the marginal distribution should be. So we can see that in this case, the sample is going a bit crazy at the moment. It's going off the screen on the left, and it's sampling way too much to the left here than it is over that region. Although in this dimension, it seems to be doing a pretty good job. So the one thing that affects this in a big way, let's see if I can start it. Oh no, don't crash. Let's see if it's still working on the other one. One thing that has an impact is the exact transition kernel that you've given it. So here, what I've done is I've made it so that the transition kernel is still a normal distribution, a two-dimensional normal. So wherever we are, we propose the next point just based on a normal distribution centered at our current location. But I've decreased the variance so that now it's proposing new points that are very close to where we were previously. And so you can see now we're actually moving around a lot more. We're accepting a lot more points, which is, in a way, is good for our algorithm. We want having rejections, having all our proposals rejected is not a good thing. But the downside is, you see how the points that it's creating are all on the left half of the banana. It's not really representative of the distribution. So maybe if you look at the histogram at the bottom here, we can see that this histogram is not at all reflecting the distribution of the curve that we're trying to sample from. It's very, it's far too much to the left. And it doesn't have enough variance. So even though this method, it works regardless of what proposal you choose. So here now I'm choosing a gigantic variance, and most of the points are being rejected. Although every time we do make a transition, we're usually moving a very large distance away. So we're going to explore the distribution in a much more comprehensive way. Even though each of these choices is legitimate for the sake of the algorithm, you get the practical differences of the kind of samples that you have coming out of them. And so this kind of transition is called that I'm showing you right now is the random walk transition. So it just, wherever you are, you sample from some distribution and add that to your current location. So you sample from a normal, add that to where you are now, and you sort of, every direction is symmetric. So you want to go, where as a contrast, it's a more modern way to sample, which is what I originally showed you here. It's doing something really crazy. So I won't make you code this because I think I would struggle to code this myself. But what it is actually doing is it's sort of, this is called Hamiltonian Markov chain Monte Carlo. And it sort of pretends that the contours of the joint density are like a real physical system. So imagine the dark blue points being like a bowl that is actually lower than the points that are white, which are the points of the areas of low probability, which are higher. And it imagines just starting wherever you are, and it imagines just rolling a ball along the surface. It picks a direction and it picks a speed, and it rolls the ball through this three-dimensional space, and obviously it's going to sort of roll downwards towards the point of high probability more often. But sometimes if you push it uphill for a while with the right force, it'll go uphill and give you a point which is one which has less probability. So I could watch this all day, to be honest. It's just so beautiful. But this is the kind of thing that you would probably not code up yourself. Each statistical library would have its own implementation of this. In Python, it's PyMC3. No idea what it would be like in R, but I'm sure someone's done this in R. Okay, so yes.
So the transition kernel is just the function, which might be a random walk. This is defined sigma or something else.
Yeah, it's a conditional density. So the two ways to look at it is, one is just as a sampling thing. You need to be able to say given where I am now, I need to be able to sample another point. And the second part is you need to be able to actually calculate the density of getting that point, because that actually appears inside the Metropolis Hastings algorithm.
And how do you fix the sigma for the one-on-one?
I'm glad you asked that question, because it's actually in your quiz this week. You're going to look at this kind of thing. Because there is no particularly magical way to do this. And obviously, once you get beyond two-dimensional problems, things get very hard to tune these parameters.
Because how do you know if you are far away from the curve or far under the curve because of the sigma?
It's extremely hard. So as I've said many times, each time I present you a new algorithm, in some ways it's much worse than everything I've shown you before. So this is it's really much a black box. Like if you run this, you really you have all these theoretical guarantees that everything is perfect. You'll sample from exactly the distribution you like, but then there's all these sort of holes that you could stumble into, and one thing you could imagine, for example, is instead of, or maybe they even have the distribution here. Yeah, so this is like a multimodal distribution. So I don't know if it's hard to see, but there's three sort of circles of high probability here. If I change back to the normal distribution, if I'm just choosing normal jumps, and the distribution that I'm trying to sample from, for example, has patches of high probability, and then between them patches of low probability, and I'm just sampling these tiny little jumps over and over again, it's really simple for your sample just to only return samples from one of those modes, and with high probability it would never ever get to those other modes. And so you'd have to either you'd run this many times and you would look at the output and say, okay, if for example you see some output where it happens to find this mode over here, you would have to say to yourself, aha, well, something's happening here. Maybe this is a multimodal thing, and try to come up with a smarter way to do it and change parameters. But yeah, it's difficult. Basically, it's very hard sometimes to know that you're doing it correctly. Okay, so I think that's the extremely short lecture 1 for today. And then I can post the quiz 3 onto the website now. And if you wanted to start on that directly or finish off quiz 2, then I can help for 1 hour, and then we can come back to do the mathematics afterwards.
Just a question on the algorithm. On a higher view, what we're trying to do is to generate some dots from the distribution.
Yeah.
We need to know on the first part the distribution, I suppose.
We need to be able to write down the density, except for except as part of the normalizing constant. If you write down something, if you write down some function and you say, is this a density function?
Yeah.
You look, is it positive? And then does it integrate to 1? If you just write down something that doesn't integrate to 1, well then MCMC will sample from the distribution which does integrate to 1. If you were to integrate that thing, it would sample from the result. And as an example, what we'll be doing is sampling from this. In the last lectures, we looked at this optimal important sampling density for rare events. And we could write down the density, except the normalizing constant was actually the probability that we're trying to estimate. So we couldn't use it. But with this technology, we can still sample from the optimal density, even though we can't write down the full thing. We can only write it down up to the multiplication.